Okay, good morning. So last class we have quickly looked at some of the signaling components of a neuron. We looked at the neuron parts of a neuron like soma, dendrite, axon, and synapse and all that. We also looked at the four signaling components: the dendritic processing, the summation in the soma, then axon propagation, then finally neurotransmission at the synapse. But last time we just looked at a big picture and we haven't gone into the molecular basis of these signaling components. So let us do that now. And that gives us a basis for mathematical formulation. That will tell us how to describe it mathematically. So like we said last time, neuronal signaling is can be both electrical and chemical. And all the signaling inside a neuron is basically electrical. But the signal that goes from one neuron to another is chemical. So let us see what is the base of this neural electricity. So a neuron can be in the resting state where its voltage is at a constant level. A typical value is like minus 70 millivolts. It can vary from neuron to neuron, minus 60, minus 80, minus 90 also. But minus 70 is a typical figure, so let us stick with that. So resting state, it remains constant, but when you excite the neuron, let's say by injecting some current, and when the voltage crosses a threshold value, like we discussed in the last class, it shows these sharp fluctuations in voltage and these sharp spikes, which are of constant amplitude and duration. They are called action potentials. So neuron puts out a series of these action potentials when it gets excited. So the convention is this voltage is always measured inside the cell with respect to outside. So I assume that outside is the external space is at ground potential or 0 volts. With respect to that, inside is a negative value. So now let us ask the question: what is the basis of this voltage? How is it generated? So any cell, like neuron, like any other cell, is permeated by a bunch of ions. So both the intracellular medium and the extracellular medium is an ionic medium. It's full of different kinds of ions. Some of the key ions are sodium, potassium, chloride, calcium, and so on. Now these ions are at different concentrations between inside and outside. The concentrations differ between inside and outside, and that creates that kind of a gradient in concentration, creates a voltage difference. Let us see how that works out. So let us consider a kind of a beaker which is filled with a solution of KCl, potassium chloride, and there is a separating membrane in the middle of the beaker. In the left compartment, there is KCl at high concentration. In the right, there's KCl at low concentration. And there's a membrane separating the two, and KCl can cross the membrane. So now if you just leave it alone for some time, as you can see that there is a concentration gradient from left to right. So KCl will flow from high concentration compartment number 1 to low concentration compartment number 2. And this will go on until the two concentrations become equal. So after that, nothing happens. So there is nothing much interesting is going on. Right now, let us make a small variation of the experiment and repeat it. So everything is just like before, just that the difference is the membrane now is semi-permeable. The membrane in the previous case is permeable to KCl, that is both to K plus and Cl minus. But now let's consider a membrane which is only semi-permeable, that is it's permeable to potassium but not chloride ions. Then what happens? So again, as you can see, potassium has high concentration on the left side, then on the right side. So it will flow from left to right. Chloride also would like to flow, but it cannot because the membrane is not permeable to chloride. Let's say you have such membranes, and it's if you assume that, this is what you would see. So because of this special arrangement, potassium will flow from left to right, chloride will not, and therefore initially, although the concentration of KCl is high on the left and low in the right, both sides are electrically neutral because KCl on the whole is neutral, right? But when the positive ions, K plus, will start moving from left to right, there will be a buildup of positive charge on the right side. So compared to the left, and that keeps on going. So the potassium flows from left to right because of a concentration gradient from left to right. But as it keeps flowing to the right, there's a buildup of positive charge on the right, in the right compartment. that creates electrical gradient which is from right to left, because there will be opposing electrical force which will be pushing the potassium charges back and resisting them from moving from left to right. So what will happen as this process progresses is that there will be an increasing electrical gradient operating from right to left direction. And there's a decreasing chemical gradient from left to right direction, because as more and more K plus goes from left to right, there's the gradient of potassium begins to weaken, because it's no more very high on the left and very low on the right. They tend to become equal. So this process will reach a point where the chemical gradient will equal the electrical gradient. At that point, potassium will stop flowing any further from left to right. And in such an equilibrium condition, you can notice that there is an increased potassium ions on the right side. Therefore, there will be a higher voltage, a positive voltage on the right compared to the left. So like that, if you take an ionic medium like this and use a semi-permeable membrane to divide the medium into two compartments, then you will see a voltage getting generated, right? So this is the basis of your battery, that all this you might have studied in your electrochemistry classes in your high school sometime. Now, how is it relevant to how voltage is generated in a cell or in a neuron in particular? Now, this semi-permeable membrane is the key feature that generates this voltage, right? Similarly, the equivalent of that in a cell is presence of this special pores in the cell called ion channels. There are little holes in the cell. So like I was saying last time, the cell is covered by a lipid bilayer, a double layer consisting of lipid molecules. Now this double layer, you can think of it as a kind of a capacitance, because this is an insulating sheet. Ions cannot just cross that sheet from outside to inside or inside to outside. Now the only way they can cross the cell wall, cell membrane, and move in and out is through these special holes, this special structure which act like holes. These are called ion channels. And these ion channels are also selective. There are channels which are selective only to sodium channels, sodium ions, so you call them sodium channels, or only to chloride, so you call them chloride channels, and so on and so forth. Some channels also allow multiple ionic species, so kind of mixed channels, but a lot of channels are permeable only to exclusively to one kind of an ion channel, or one kind of an ion. So you have very similar arrangement in a cell membrane, similar to your electrochemistry setup. So because of that, any difference in ionic concentration can give rise to a voltage difference, right? And a generation of a potential generated because of this kind of an ionic concentration difference is called the Nernst potential, so given by this formula. So if you have two compartments separated by a semi-permeable membrane, then the voltage difference between these two compartments, V1 minus V2, is given by this formula, that RT by ZXF times ln X2 by X1. X2 and X1 are the concentrations of the ion that is of interest here. So here the ionic species that we'll be considering is the one which is to which the membrane is semi-permeable. In the KCl case, since it is a potassium that is able to cross the membrane, the voltage generated by the potassium concentration. So chloride doesn't come into picture. So so here it is ln of X2 by X1 times R is the ideal gas constant, T is absolute temperature, Z is the valence of the ion that we are talking about. In this, if it is potassium, it is a +1. If it is chloride, it is -1. Then F is the Faraday's constant. So just for as an example, we take temperature to be 25 degrees centigrade, like a room temperature, and valence is, let's say, +1, Zx is +1, like in case of potassium. RT by F turns out to be 26 millivolts. Just to give you an idea of what is the order of magnitude voltages that we are talking about when it comes to the cell membrane, the voltages that are generated in the membrane or across the membrane. So therefore, the equivalent circuit of an ion channel, so ion channel is something that allows ions. The equivalent circuit is generally given as a conductance in series with a battery. This battery is corresponds to the voltage that is generated by this ion concentrator. Please mute yourself. Right, and so it's called the Nernst potential. So the battery value is denoted by E Nernst, and then the conductance which is in series with it is called G or G channel. Now you might be wondering, why are these in series? Why can't they be in parallel? So let us consider what happens if they are in parallel. So let us say you have conductance. And see, consider series and also consider in parallel. So imagine a situation where the channel is completely closed. So that means, so closed channel means G is equal to 0 or the inverse of G, right? R is equal to infinity. So it becomes an open circuit. So when it is an open circuit, so nothing can enter. So current cannot go in, right? If G is 0. So you have two possibilities. If it is the parallel circuit possibility, right? Even if this is closed, current can still go through this branch, right? So that doesn't make any sense, because if it is a open circuit, then nothing will go in. So this is the correct representation, because when the channel is closed, right? If they're in series, once it is when the channel is closed, that is, the circuit is open, and if they are in series, then current will not be able to go through. So therefore, this is correct, and this is wrong. All right. So now, so we just talked about channel opening and closing, because these channels are not constant fixtures. They can open and close. That means the conductance can be varied, right? And this control of the conductance of the channel can be done by many different mechanisms. So this picture shows 4 mechanisms. The print is a bit light, but I hope you can read it. The first one is called ligand gating. So gating is the general term which is used to denote control of the channel, how the channel conductance can be controlled. So ligand gating means controlling the channel opening with the help of a chemical. Right here, ligand is the chemical, and using it to control the channel is called ligand gating. And this is what happens in case of neurotransmission. The second one is phosphorylation gating. That is, you can attach a phosphate molecule to the channel, which can open the channel. The third one is voltage gating. That is, you can apply a voltage to the membrane by some other means, right? And that can also open the channel, or even close an open channel, depending upon how the voltage goes. We'll see all that in the next class in more detail. The last one is the simplest kind to understand. It is called the stretch gating, right? Which is basically, it's like, imagine there is a little hole. Imagine you have a rubber sheet. There's a hole in the middle of a rubber sheet. Now, if you stretch the rubber sheet, then the hole also expands a little. So that's as simple. The mechanism here is as simple as that. So this kind of a mechanism is useful in more practical sense in transducing the touch sense, because just imagine how the touch sense will work. That when you touch the skin, right, some signal must be going from your skin to the brain, informing you that your skin, some point of your skin is being touched. Now, how do you think that kind of so any signal that goes from skin to the brain must be in the form of electrical signal, because that's what can propagate through the nerves. So how is the touch converted to electricity? Right, you can see the clue lies in this last mechanism. So when you touch the skin, there's a pressure applied to the skin or skin cells. So skin cells also have this kind of stretch sensitive ion channels, and because of the pressure, these channels open. That creates a current which goes into the cell or outside the cell. So like that, the touch stimulus or a mechanical stimulus can be transduced into an electrical signal. So this 4th channel figures in that process in a big way. So there are 4 types of gating, but as far as our requirements are concerned, we will focus mainly on 1 and 3, that is ligand gating and voltage gating. So like we just said, the channel can be represented electrically as a series of a conductance and a nonce potential, a battery. And conductance can be varied, and therefore to denote that we use this arrow. This arrow cutting across the conductance indicates that it's a variable conductance. Now let me also say that all conductances are not variable. Some conductances are fixed, right? There is no gating, but some are some are gated. Okay, and when they're gated, there are different kinds of gating, which is what we discussed in the previous slide. Okay, so now let us look at the kind of concentrations that exist for sodium and potassium, because in the generation of the membrane potential, right, in the generation of the electrical activity of a neuron, the 2 major players are sodium and potassium, and these are also the ions which play a major role in the most popular neural membrane model, which is Hodgkin and Huxley model. So we'll discuss that in the next class. So let us consider the typical nonce potentials that are associated with potassium and sodium. Now the thing is, under resting conditions, when the neuron is in resting condition, so let's say this is a neuron. Under resting condition, sodium outside is high and sodium inside is low. And a resting condition, potassium outside is low and potassium inside is high. So there is a opposite relationship between sodium and potassium. Therefore, if you look at these numbers, potassium outside K plus O is small, potassium inside K plus I is large. So if you plug in these values in this formula, you got a potassium nonce potential EK of the value minus 77 millivolts. Also, a typical figure for the conductance of potassium is 36 millisiemens per centimeter square. So you know that the units of conductance is Siemens, but why this centimeter square per centimeter square? So for that, the answer is, so let us think of the cell membrane as a sheet, right? And so there are lots of conductances because there are so a lot of conductances, a lot of ion channels inside this sheet. Right, so let's say each of them has some conductance G. Now, since all these channels are stuck inside the same membrane, right, you can think of them as as being present in as a parallel, because they're all across the same membrane. So voltage here is inside is same Vm. It's called membrane voltage. Voltage outside is 0 by convention. So they all have same. They're all in parallel. So when you have conductances in parallel, what do? The total conductance is simply the sum of all the conductances. So therefore, when we want to decide on a unit for the conductance, right, millisiemens means you're talking about a set of conductances. But a better way to talk about the membrane or the neural membrane is simply to talk about a membrane of unit area, right? Some unit area, one by one. So therefore, the conductance will be the conductance of a arbitrary area by the area of the by membrane of an arbitrary area by the area of the membrane, right? So we talk about conductance per unit area of a membrane. So therefore, we use units that are used for conductance is Siemens or millisiemens per centimeter square. So for potassium, a typical figure under resting conditions is the nonce potential of value Ek is equal to minus 77 millivolts, right? And the conductance value is 36 millisiemens per centimeter square. So if you plug these 2 things here, right? So this is the equivalent circuit of a potassium channel. Similarly, for sodium, the like I said, sodium is high outside and low inside. So it is 450 millimolar outside and 60 millimolar inside. So if you plug these values here, you get TNA is equal to 50, and a typical value of millisiemens of the potassium sodium conductance is 120 millisiemens per centimeter square. So therefore, for the equivalent circuit of sodium can also be given like this with these values. Now, so sodium potassium, there are, we use these what are called voltage sensitive or voltage dependent sodium channels, because we talked about 4 kinds of gating. We said we'll be mainly using 2 of those mechanisms of gating, which is voltage gating and ligand gating. So in this context, let us talk about voltage gating. That is, therefore, we'll consider sodium potassium, which are voltage gated or voltage gated sodium potassium channels we'll be using. Then in addition, there are other channels in a typical neural membrane which are not gated at all. These have constant conductances, and such channels are called leakage channels, right? So therefore, the sodium potassium channels we'll be using are voltage dependent channels, and there are other channels which are called leakage channels. So if you combine all this and try to put together a model of the neural membrane, right? You have sodium channel, right, which has some conductance and a battery, and a potassium channel which has a conductance in the battery, and then a bunch of these constant channels that are called leakage channels, right? Imagine there are lots of them, and we don't care exactly what channel type they are. So I just call them ABCD and so on. So they're all there, and each of them has their own conductance and battery, inertial potential, and all that. But only thing is they're all constant, so I don't have the arrow cutting across the conductance. So you have a whole bunch of them. They're all also in parallel. Now, the beauty is I don't have to represent all of them independently. I can just combine them and come up with some kind of a net equivalent of all those channels, because from electrical engineering we have this very nice theorem called Thevenin's theorem, which says that if I have a bunch of these passive electrical elements, I can combine them into an equivalent circuit consisting of a resistance and a battery, or in a conductance and a battery, both are the same, right? So with that nice theorem, I'll just assume that all the leakage channels can be combined into one branch, which has certain noise potential and certain conductance. And that value for a typical neuron, actually we are talking about the neural membrane which is studied by Hodgkin and Huxley. That value is EL is, that is the noise potential of leakage channels, is 10.6 millivolts, and the GL is the conductance is pretty low, is 0.3 millisiemens per centimeter square. Okay, so then there is a fourth element so we looked at sodium, potassium, and all the leakage channels. We have put them together, clubbed them together into one branch, mathematical equivalent of all of them together. Then finally we have to consider the one missing thing which we ignored until now, which is the membrane itself. So all the channels are attachments to the membrane. They are something that is stuck inside the membrane, right? They have some electrical properties. We have seen that just now. But the membrane itself is also has an electrical property. Like I said, it's like a parallel plate capacitor. It's an insulating double layer of these lipid molecules. These are molecules. They have these heads and tail and so on. So they are arranged like this. You can think of it as a parallel plate capacitor. So if you put all these things together, and you see that all these things are across the same two media, right? All the channels and the membrane itself are across two media. One is extracellular space, another is intercellular space. So therefore, they have the same voltage difference between the two ends of them. Right. For this reason, you can put them all in parallel. The capacitance, the sodium channel, the branch consisting of a series of conductance and battery, and potassium channel, which is the branch consisting of the conductance and the battery, and then the leakage channels, a bunch of them all put together and represented as another conductance and a battery in series. So all these 4 branches are in parallel, right? And this can be a pretty reasonable model of a neural membrane. So this can be used to understand how action potentials can be generated, right? How a membrane potential can be generated, and so on and so forth. So we'll be coming back to this in next class in more detail. Well, let us do some simple hand calculation to get an intuitive idea of how the membrane potential is generated or even varied, right, by varying these two circuit elements. There is a conductance of sodium and potassium. So these are the two key players in controlling the membrane voltage, and let us get an intuitive understanding to see how these two can control the membrane voltage. Like again, I want to say that this is just a very rough calculation. It is not strictly mathematically valid, but just to give an intuitive understanding. So imagine that this whole circuit is in steady state, right? Then let us try to understand the value of the so inside this inside is outside. The outside is actually 0. So ideally speaking, you should draw the circuit upside down, but we'll draw that later. And this is the kind of circuit you will see in a lot of biology textbooks, neurobiology textbooks. I'll draw it slightly differently later, right? Which means the voltage inside we denote it by the notation Vm, also shown here, and the outside is 0. So this is ground. Okay, so now how do you express Vm as a function of all the other circuit elements under steady state conditions? So under steady state conditions, all the voltage and currents are constant. Right now, you know that under steady state condition, the capacitance does not pass any current. That's right, because when voltage is constant, current in capacitor is C dV by dt. So current will be 0. So if current is 0, then I can ignore this branch. Then I am left with only these 3 branches consisting of batteries and conductances. And you can easily apply your Kirchhoff's laws and calculate that under steady state conditions, Vm is given by this formula: GNA ENA plus GK EK plus GL EL by GNA plus GK plus GL. So how do you do that? You can just kind of, when you have just these 3 branches, right? Right, the total current into going into all these branches should be equal to 0. Apply Kirchhoff's current law at this node or this node, then that you will get by doing this: Vm minus ENA times GNA plus Vm minus EK times GK plus Vm minus EL times GL is equal to 0. So if you solve this, you get this formula. Okay. So so now consider what happens, right? Consider 2 situations. So we said that GNA and GK are variable because you have the arrows here. You can, let's say, by some mechanism you can control them. You can also control them independently, let us assume. Right now, consider a situation where GNA is high and both GK and GL are low. Right. So then what happens? What that means biologically is the sodium channels are open because the open channel has high conductance. Intuitively, a closed channel has low conductance. So imagine that GNA is very high and compared to GK and GL. Then what happens is in this, you see that ENA, EK are all in the same order of magnitude, right? So now if you increase the GNA abnormally, then this term will dominate the other 2 terms, both in the numerator and denominator. Then this voltage formula approximately becomes, GK is much higher than the other 2 conductors. Let's first consider GK, right? Then the GK EK term will dominate the numerator and GK term will dominate the denominator. So then you get this approximation. So if you cancel off GK, you get EK. So what that means is, when the potassium channels are open and sodium channels are closed, that is when GK is much greater than other channels, and GL is always a small number, so that doesn't even figure in the comparison. So then Vm becomes close to, right, EK, and EK is minus 77 millivolts. So Vm goes close to that value, right? And interestingly, this is what happens in the neuron's resting state. And so also, it is not that sodium channels are completely open and potassium channels are completely closed. So what happens in the resting condition is more potassium channels are open and more sodium channels are closed. So therefore, Vm goes close to the minus 77 value of EK, and actually it is equal to minus 70 millivolts in the resting conditions. Now consider the opposite condition where the potassium channels are closed and sodium channels are open. So GNA dominates both denominator and numerator. So therefore, Vm can be approximated by this formula, right? And if you cancel off GNA, you get ENA. So what that means is, if mostly sodium channels are open, then Vm goes close to ENA, and ENA happens to be 50 millivolts plus 50 millivolts, right? And therefore, Vm will be something closer. Typical value is about 30 millivolts. This is the kind of value to which the membrane. This is kind of the maximum value where the membrane voltage approaches, right, during its fluctuations. Okay, so what we understand by the simple, just loose arguments, is that if you want to increase Vm towards positive values, open more potassium channels, and if you want to decrease Vm and keep it close to -70 or take it even lower than that, open more potassium channels. So basically, sodium potassium channels act like two knobs, right, by which I can increase and decrease the voltage, membrane voltage. Now let us see what happens when action potential is generated. So we described this in the last class. So if I give a small current input, inject a small pulse of a current into a neuron, when I give a small input pulse, then the voltage also shows a small blip and comes back. As I progressively increase the current pulse amplitude, right, the voltage pulse also keeps increasing progressively. But once my current pulse amplitude crosses a certain threshold, the voltage doesn't simply increase linearly, but shows abnormal nonlinear response, where it goes produces a large positive excursion, goes to positive values, right, and also quickly comes back and goes to a value which is even less than this baseline value of -70, stays there for a little while before coming back to the baseline value of -70. So this is called an action potential. So how is it generated? So so what happens is when a current is injected into the soma or into the cell membrane, the local membrane potential increases, which we have seen in this graph. Right, when the current is injected, positive current, the voltage also goes up. So what happens is, like I said, both the sodium potassium channels are voltage dependent. They can be controlled by voltage, and particularly sodium channels can be the conductance can be increased. They can be opened by increasing voltage. So when you inject some current, that opens the sodium channels. Some more sodium channels. And we have also seen with our loose arguments that opening sodium channels will increase the membrane voltage further. Right. So the original injection of current opened some sodium channels, and that in turn has increased the membrane potential. That in turn will open more sodium channels. So you kind of initiate a positive feedback situation by which sodium channels can quickly open. Now that's what happens on the sodium channel side, right? But but on the other hand, what happens is the same increase in voltage also opens potassium channels. Now we've seen that when you open potassium channels, that will decrease the membrane voltage. So that will involve a negative feedback. Let me say that. Right, so that will kill the whole process. So initially sodium channels open, and that will involve a positive feedback, so it will keep on increasing. But the same increase in voltage also opens potassium channels, but opening of potassium channel will decrease the voltage, so that will initiate a negative feedback process. The only thing is the time scales involved in opening the sodium channels are much smaller, right, than time scales involved in opening the potassium channels. So therefore, when you inject a current, initially sodium channels open, right, they keep on opening further and further because of positive feedback. But after a little delay, a bit slowly, potassium channels also start opening, and that will kill the voltage. And potassium channels have a greater effect in this process. So because of these two opposing processes acting on a slightly different time scale, what happens is that initial injection of current will, especially if it is sufficiently strong, it will initiate a rapid opening of potassium channels, which causes a rapid increase in the membrane voltage and takes it to positive values, followed by again opening of potassium channels, which will give rise to a rapid decrease in the membrane voltage, right, and then followed by a return to the baseline value. So all this happens very rapidly. Therefore, you see a sharp rise and a sharp fall of the membrane voltage, and this kind of a spiky voltage waveform is called an action potential, or AP. And the duration of this in mammalian neurons typically is about 1 millisecond. Interestingly, a lot of plant tissues also have action potentials, right? Plants also have some kind of a primitive nervous system and some kind of electrical signaling system, and they also have action potentials. Only thing is they have very slow action potentials. Their APs can be as long as a couple of seconds. And all of this was worked out by Jagdish Chandra Bose, great Indian scientist, almost 100 years ago. Okay, so just to recap, what all happens when the action potential is generated. Initially, when you inject some current, that opens sodium channels, right? That will make sure sodium ions go from outside to inside, right? That will increase the membrane voltage. That will open more sodium channels. That will increase the voltage further, and that will slowly now start opening the potassium channels, which will cause reduction in the voltage, and that will start closing the sodium channels and opening more potassium channels, right, and so on and so forth. So that will, all these processes occurring one after another will give rise to a sharp rise and a sharp fall, which is action potential. So this picture shows how the voltage varies, voltage underlying the action potential. And in the process, we said the sodium channels open and close, and the potassium channels also open and close. So which means when they open, the conductance is high, when they close, conductance is low. So the conductance variation of the sodium potassium during this whole process is given by these two curves. So GNA, that is sodium conductance, right, rises quickly and also falls quickly, as shown in this second curve, right, and GK, which is potassium conductance, rises slowly and falls even more slowly, which is shown by this dark curve in the bottom. It is this difference in the delays and difference in the amplitudes, right, that causes this nice voltage waveform that we call action potential. Now, what is so nice about action potential is that so it is generated by nonlinear dynamics occurring inside the circuit. So in both cases, right, we have seen that between the membrane that is inside the cell, outside the cell, there are conductances and a capacitance. That's all there is. But what happens is when the conductances are variable, and especially when they are voltage gated, like in the case of sodium potassium channels, voltage in turn can control the conductance. So normally, if a conductance is follows Ohm's law, so that is V equal to IR if it is resistance, or I is equal to GV, which is if we talk in terms of conductance, you know that R equal to 1 by G. So now this is Ohm's law, right, where G and I is a constant, G and R are constants. But imagine a situation where I is equal to G, which is a function of voltage, and then multiplied by voltage. Now the voltage current relationship will not be a straight line, obviously, it will be some kind of a curve. It's nonlinear, basically. So because of that nonlinear dependence, right, the presence of this kind of non-ohmic conductances, right, the circuit is able to generate this sharp voltage spike, which is action potential, and has no connection to the input pulse. Right, input pulse is the same rectangular pulse, but the output will be this action potential, and that kind of a response is possible because of presence of this kind of nonlinear elements. Now, this kind of voltage-dependent channels are not present everywhere in the neuron. They are present only in some places, and wherever they are present, the neuron is able to produce action potential. And wherever they are absent, you won't have action potentials, right? The circuit will look like this. That is just a parallel between a conductance or a resistance and a capacitance. In that case, what happens is if I give a increasingly stronger input current pulse, the voltage also will just increase and drop. It won't produce action potentials. And this is what typically happens on the dendritic side, right? And on the this is what typically happens on the axonal side. Therefore, axons have action potentials, but dendrites don't. Okay. Having said that, let me also quickly make a correction, right? That these general patterns are only like simplistic textbook patterns. In reality, you can have voltage dependent channels even on the dendritic side. You can, in principle, have action potentials, but by and large, the typical feature pattern is action potentials on the axonal side, but no action potentials on the dendritic side. So all this, the underlying mechanisms, the molecular mechanisms of generation of an action potential was studied by Hodgkin and Huxley, the British physiologists, and they got a Nobel Prize. They'd done their work during the 50s, and their work got them a Nobel Prize in 1963. So for their studies, they used this large animal called the giant squid, right? And because it has a large axon, a thick axon of about almost 2 millimeters. So they didn't have microelectrodes required to penetrate very small axons, right? Like a typical mammalian axon, like is about a couple of microns. So it's very hard to make electrodes which are so small. So that's something about action potential. Then, like I was saying last time, once an AP is generated in the axon hillock, it propagates down the axon, and like I was saying last time, the action potential propagation along the axon is intact. It doesn't lose its amplitude and shape, and that's again because of presence of voltage sensitive sodium potassium channels, which are present all along the length of the axon. So therefore, thing is normally when a wave propagates along a wire, along the cable like this, because of resistive elements in the cable, it loses energy, it dissipates energy, and therefore it loses amplitude. But presence of voltage sensitive sodium potassium channels is like, so since they are nonlinear, they are like active electrical elements. They can inject energy into the signal, into the circuit. So therefore, they are able to charge up the action potential as it is propagating, and they keep it intact, and it's able to propagate intact along the cable. So here again, there's an even more interesting process that takes place. Some axons are endowed with a special insulating sheet, a coating, right, which is which is made up of a material called myelin. So this kind of a myelin sheet gives it better insulation, so that the charges from inside the axon don't leak out into the ECS. So that means there is you don't lose the signal energy much because of this insulating coating. Just like you have a plastic or a rubber coating on electrical wires, right? You have this coating of myelin around axon, a lot of axons, not all, but many axons. So when the signal propagates, action potential propagates along the axon, right? Because of this presence of this insulating sheet also increases conduction velocity. So we'll see that later in the course, right? So conduction velocity is higher when there's myelin sheet. So therefore, this action potential propagates rapidly in this stretch where there is a myelin sheet. And this myelin sheet is also offered by other kind of cells called the oligodendrocytes in the central nervous system. So this is a cell, this is a cell. So there is a little gap between these two cells. In this gap, the axon is exposed. There's no myelin sheet. And in this gap, you have you have higher density of voltage sensitive sodium potassium channels. Therefore, the signal rapidly propagates under the myelin sheet, arrives at this gap. This gap is incidentally called, these gaps are called the nodes of Ranvier, after the guy who discovered them, I suppose. So here the signal gets charged up because of the voltage sensitive sodium potassium channels. And after that, again, it rushes from underneath the myelin sheet. Again, it arrives at the node of Ranvier, where it gets charged up, and so on and so forth. So it is a very complex, very optimized, highly optimized machinery for making sure that the signal propagates intact without losing its shape and size, right, as it propagates along the axon. And since this propagation occurs at a slightly non-uniform velocity, because rapid motion under the myelin sheet, little delay in the node of Ranvier, again rapid motion under the myelin sheet, and so on, it looks as if the signal is jumping from one node to the next node, right, because of the rapid propagation under the myelin sheet. Therefore, this kind of propagation is called saltatory conduction. Saltatory has nothing to do with salt. Apparently, it just means jumping, right? So the AP jumps from node to node. Because of this kind of a complex arrangement, the propagation of an AP is faster in myelinated axon. The typical conduction velocities are like this. Unmyelinated axons about 0.2 to 2 meters per second, right? Myelinated axon is 12 to 120 meters per second. So note that these velocities are much smaller than the velocities that propagation that you see in a electrical cable, because the current in electrical cable is electronic current, and the current in the neural cable is ionic current. It's carried by ions, which are much heavier elements. So the axon propagation is can be seen in this simple animation. The action potential propagating intact without losing shape and size along the axon. Now, on the other hand, on the dendritic side, there are usually no voltage sensitive ion channels. Therefore, there is no mechanism, molecular mechanism to charge up the signal as it propagates down the cable, because you can think of the dendritic cable like this. It's a bunch of resistors in parallel, in series, and so this is the cable, this is the dendritic cable, as shown in this figure. Right, and from inside the cable to the outside, you have R and C, or conductance and capacitance in parallel, right? And so on the axonal side, you have the voltage dependent channels, but here there's no voltage dependent channel. Therefore, the whole thing is just a purely passive cable, right? A passive circuit. So if you inject some current into the circuit somewhere, so I, which is like a I of t, which is like a pulse, then you can easily notice that this energy gets dissipated in all these resistors present everywhere. And if you measure the voltage from somewhere here, V of t, you will see that you will see a loss of voltage. If you measure it here, it will be higher, but if you measure it here, it will be lower because of all the energy loss and the resistances on the way. So therefore, propagation along the dendritic cable is lossy. It looks something like this. The signal waveform loses both amplitude and spreads in time as it propagates down the dendrite. Now, finally, let us come to the neurotransmission, the last step at the synapse. Like I was saying in the last class, at the synapse, you have the presynaptic terminal and the postsynaptic terminal. The action potential comes to the presynaptic terminal, where a chemical is released from the presynaptic side to the postsynaptic side. On the postsynaptic side, the chemical acts on the terminal and produces a PSP. So let us see how exactly this happens. So like I said, there's a chemical step here. The chemical is released. So in this whole, which is called neurotransmission, there's actually three molecules, molecular players, which play a major role in this neurotransmission. The first one is the chemical released by the presynaptic terminal. That's called a neurotransmitter. All right. Then the neurotransmitter, once it goes to the postsynaptic side, it acts on another molecule which is called a receptor, and this receptor is usually associated with an ion channel, right? The event of binding of a neurotransmitter and a receptor causes either opening or closing of an ion channel, which is a third molecule, right? And the opening or closing of ion channel then will cause a current to flow, or ongoing current will be stopped, and that will change the membrane voltage on the postsynaptic side. So you see that this is how you convert a presynaptic voltage signal into a postsynaptic voltage signal. So the first event is when the action potential comes to the presynaptic side. The neurotransmitter is normally packed inside small packets called vesicles. These are called the synaptic vesicles. And when the AP comes here, these vesicles, which are normally locked inside a protein complex here, the protein complex is broken by this increase in voltage, and these vesicles will start drifting towards the membrane, right? They start moving towards the membrane, and then the vesicles themselves have a membrane, right? This membrane now fuses with the membrane of the synapse, right? And then the vesicle splits, it opens, and then releases its contents into the synaptic cleft. This is synaptic cleft. This gap is called the synaptic cleft. And then these neurotransmitter molecules then drift or diffuse across the synaptic cleft, go to the postsynaptic site. And on the postsynaptic site, they bind with the receptor. Right here, you can see that this molecule is binding with the receptor. In this case, the receptor is itself a part of the ion channel. Okay, so a part of the ion channel acts like a receptor, and once that binding takes place, that binding event opens the channel and current flows in. That will change the voltage on the postsynaptic side, and which is what you see in the form of a PSP. So there are three molecular players: the neurotransmitter, receptor, and ion channel, right? And here again, there are two different kinds of receptors. Acts like a receptor. So the